Okay, now let's move on to the next gas, ammonia. So ammonia is one of our very, very important industrial gases. So when you look at this graph, so ammonia is the #1 chemicals globally produced. Okay, because this ammonia is almost 80% of ammonia can be utilized as a fertilizer. So if there's no ammonia production, maybe many people get starved and die. Okay, so to produce the ammonia this much, so actually the CO2 gas emitted quite a lot. Okay, so it actually caused very significant carbon print. That is the negative effect anyway. And also when the ammonia leakage happened, so in Korea here, so this is the chemicals that the forms of fine particle matter. Okay, and also the ammonia leakage causes the health problem, as shown right here. Only 500 ppm exposed causes immediate death. So that means this is really high toxic, and then it is necessary to absorb CO2, the ammonia at very low the ammonia pressure as well as high pressure. So ammonia is a base, so you can use open metal site as well, because open metal site is less acidic. So some people utilize this kind of material because it has the open metal site, and then using this material, the capacity is almost 20 millimole per gram. This is very high. However, as I mentioned before, the high capacity at a ppm level is very important. So to actually protect human being from the ammonia leakage, and also chemical stability in wet ammonia condition. So this is also important. So again here, we actually utilize the M2DO-PPDC, the platform containing high density of open metal site. Okay, so you have a high density open metal site. So we expected to get very high the ammonia capacity due to the presence of a high density open metal site here. Okay, so this is ammonia adsorption isosome at very low pressures. So I want to show this correlation diagram and also comparison data right here. This is this work, okay, at very low pressure, below 1 millibar. So actually magnesium 2-DO-PPDC exhibit highest ammonia capacity at very low pressure. Okay, so you can compare the reported cases. At the same time, at 1 bar, this material exhibit capacity of 23.9 millimole per gram. So this is at 1 bar. This is the highest value among the reported cases. So we checked the Lewis acidity of open metal site because we utilized the many metals. So as shown right here, so this is the ammonia temperature programmed desorption data. Okay, so you absorb the ammonia, and then you increase the temperature to track down the ammonia, the concentration. Okay, here the nickel the exhibit the highest Lewis acidity, followed by magnesium, cobalt, and manganese. And that stability against the wet ammonia is important. So we check the stability upon exposure to wet ammonia. So as shown right here, manganese right here shows the stability even under wet ammonia. And the other analog shows structural collapse. Okay, this is quite interesting because nickel looks like most stable in the series, but in reality, magnesium shows most stability. Why this happened? So we just picked out nickel and magnesium stuff to compare why that happens. Okay, so we carried out DFT calculation with the help of Dr. Jung-Hoon Lee at KIST. So this is the framework, and when you look at this one, actually this metal is surrounded by 6 oxygens. So you can get the MO6 octahedral geometry right here. So we mimic MO6 octahedral geometry by using metal hydroxide right here. Okay, and then we made the modeled the ammonia, the complex right here, and then we obtained the formation energy of a reaction. So here magnesium shows a positive value and nickel shows a negative value. So this means that this reaction does not happen in magnesium, but does happen in nickel. So that's why in the presence of ammonia in the humid condition, nickel shows the structural the collapse, while magnesium is okay under the same condition. And the other the interest in our group is ammonia as an energy vector. So ammonia can be utilized as the hydrogen carrier. So you can get hydrogen or energy out of ammonia. So it is important to store ammonia very safely. So here we actually interested in adsorption the method to store ammonia very safely and also a lot. So here, so these are examples showing high uptake. However, the regeneration temperature is very high. That is not good for the getting ammonia out of a framework. And also there is a trade-off between gravimetric and volumetric capacity here. For example, M2DO BPDC exhibit highest the gravimetric ammonia capacity. However, volumetric the capacity is quite low. But in this case, gravimetric capacity is very low, but volumetric capacity is very high. So you want to get very low regeneration temperature, and you want to get very high gravimetric capacity as well as very high volumetric capacity. Yeah, that would be really great as an ideal ammonia adsorption the material. So here we are interested in these material because there are two important point right here. So this material has open metalsite right here, and also bleaching chloride. What happened here is that this bleaching chloride can be replaced by hydroxide or bromide as well. So this bromide could be utilized as another, active site. So our goal is to increase both gravimetric, volumetric capacity, and to decrease the regeneration temperature by using bleaching ligand being replaced to incorporate carboxylic group. This is acidic, so it is easy to get the ammonia. So this is the post-synthetic modification route. So you have a pristine one, and we the reacted acrylate to replace the chloride with this acrylate. Okay. After that, this double bond is reacted with the sulfur-containing ligand by N-siol click reaction to get the carboxylate right here. And we carried out the structural determination of this acrylate containing material, and we are successful in doing it. So as you can see right here, chloride is gone, and instead you have acrylate right here. So actually you can see here chelate and bridging mode by acrylate. Actually, this is a new type of the materials, and replacement of chloride by the carboxylate. And then the ammonia capacity here at 1 bar is 23.5 millimole per gram. So this is quite significant, almost a record value. And then we regenerate this material at mild regeneration condition, like a vacuum room temperature for 12 hours. So this material shows, anyway, the very low regeneration energy. So this is a favorable and required property for real application. And then we check the volumetric density here. So right here, this is our material showing very decent the properties right here. Okay, so the volumetric one, that's good, and colorimetric one, that's good. So this is quite promising adsorbent, we believe. And then we checked the ammonia adsorption mechanism by using in situ IR data. So actually these peaks indicate the presence of nickel and ammonia, the coordination bond. Okay? But in this sample with acryl TMA, so TMA here means that you have two carboxylic acid group. So in this case, you cannot see this kind of stretching frequencies and bending frequencies. So this means that there's no nickel ammonia, the coordination bond. Okay. So here we checked 4 samples because this is a pristine sample and this is acrylate, and the other one is obtained after N-siol click reaction. So TJ indicates 1 carboxylic acid, TMA indicates 2 carboxylic acid. So in 2 carboxylic acid sample, there's no nickel ammonia coordination bond. So this is what I want to mention in this slide. So here, so this is a pristine sample, so you can see nickel and ammonia bond very clearly. So this is a nickel acrylate sample, so you can see this is ammonia. So this ammonia is coordinated to open metal site, and also there is a weak interaction between the hydrogen and carboxylate oxygen right here. And so this is a TMA sample. So in this case, there's no the metal and the ammonia, the coordination bond. So this is due to the bulky, the group of 2 dicarboxylic acid. And then, as shown right here, so actually in this case, okay, so you have a very low dissolution temperature. That means ammonia can be regenerated at very low temperature compared to others. So here, when there is the coordination bond between the metal and ammonia, so you need to get very high regeneration temperature. But in this case, there's no such bond. So that's why the regeneration condition is very mild. Okay, so this is a recyclability test. So again here, the pristine sample with the high density open metal site shows, the first cycle is okay, but second cycle you can see very low capacity. That means the coordinated the ammonia cannot be regenerated under this condition. However, so TMA 2 carboxylated one, you can see very good recyclability. Okay, so I have time. Okay, this is the 2 minutes. Okay, so I'm going to talk about ethane ethylene separation, the work carried out in my group. So this ethylene is industrially very important the gas, because it is utilized as a monomer for polymerization. But during the thermal cracking of hydrocarbons, so actually there is an impurity, the ethane among the ethylene. So this ethane should be removed to get high purity ethylene. However, the cryogenic distillation is industrially used nowadays, but this is energy intensive, so should be replaced by another techniques. So here, I want to introduce the adsorption-based separation of these important gases. Okay, there are two things should be considered. The ethylene shows a high quadruple moment, so therefore the polar environment is important. However, in the case of ethane, polarizability is very high, relatively high than ethylene, so therefore non-polar environment is important for the selective adsorption of ethane. Okay, in this slide, so there are two types of materials for separation. The first one is ethylene selective material. The second one is ethane selective materials. So here, ethane selective material is much better because you just go through one-step purification to obtain pure the ethylene, the gas. Okay, here we try to actually pick out very promising the MAP platforms, but there are many MAP structures out there, so you don't know which one is the best. So actually, with the help of the Yongchol Jung in Busan University, actually he screened many the MAP structures. Finally, he came up with these three structures. So we actually take a nickel complex first, and then we prepared this one. So actually this is actually ethane selective material. So as expected based on calculation. However, here is actually the propulsion materials, but cobalt sample is unstable even under activation condition. So to solve this problem, because this is unstable, we put the amino group right here. So using amino isonicotinate, so to make the isostructural the product right here. So here this amino group can form intra and inter-net hydrogen bond. This hydrogen bond make this material stable under activation conditions, and then we obtain the ethane selective the properties as well. So we check the interaction site why actually ethane is more selective than ethylene. So when you look at this the molecular model, So you have more CH5 interaction in ethane than ethylene. That's why this material exhibit ethane selective the behave. So we also checked the dynamic separation property using mixed gas here by a breakthrough experiment. Okay, so finally, so this is a summary. So in this seminar, I talked about CO2 capture, ammonia adsorption, and separation of these gases. So here we apply the post-synthetic modification and pre-synthetic modification techniques. So this is really successful. So as chemist, you can do that to address any problems, I think. Okay. Finally, thank to my group members and collaborators and also funding agencies. And thank you for your attention.